Okay, thank you much for inviting me. So what I'm going to do is to review some work which we done last year with Simon Jombi and Matteo Beccaria in these papers, and it will be mostly review, and I will include some basic stuff as well. So let me know if I should speed up at some point. There will be some overlap with the talk by Luigi, and also a little bit with Kim Young yesterday. So we'll see. So let me start with a very basic question, namely one of the main open questions is how to understand how to go beyond perturbation theory in some even simplest field theories, namely how to sum series in lambda, how to find coefficients of 1 over n expansion to any order exactly in lambda, small lambda, large lambda. So there was a remarkable progress recently towards this goal using combination of methods, and in particular in planar limit its integrability. Then for some special observables, localization gives us information about free energy or Wilson loops. So they then we know them exactly in gauge coupling and N. Also, there are some constraints coming from bootstrap and general principles. So all sorts of methods. So from on the other hand, AdS CFT gives an independent source of information. If you look at dual side, on one hand we can check AdS CFT. On the other hand, we get information about some other limit, like strong coupling limit in strong coupling expansion. So the basic controllable examples are again N=4 theory and ABGM theory, which will be my main focus. So here again, integrability allows us to get some information, some understanding of planar limit, and in fact there was quite substantial progress in the last more than 10 years. But one of the main open questions is how to go beyond planar limit, and that not much was done in that direction from a dual side, from AdS side, and obviously because it's hard to go beyond tree level in string theory, you need to compute loops, and again, not much was done. So this is just a reminder what kind of parameters we have in N=4 theory. Here I'm just focusing on N=4. So we have two basic parameters, Young-Mills coupling and N. On string side, we have G string and tension. So that will be my notation. That's why I'm just showing this. So in G string is related to square of Young-Mills coupling. Tension is related to 't Hooft coupling. So these are basic definitions. And we'll be interested in equivalence kind of in 't Hooft limit and in large n expansion and fixed lambda, but I also will discuss later, if I'll have time, instanton correction, so beyond just large n expansion. So integrability, just again to give a broad picture of what we know, allows us to compute spectrum of classical states in N=4 in AdS 5s5 theory or in dual of AdS 4CP3 in the case of ABGM theory. So what we're interested in is anomalous dimensions of operators, like, for example, this one, the operators with large quantum, generic with large quantum numbers, here large spin, and that gives us famous observable, which is called cusp anomaly, cusp anomalous dimension. This function f of lambda, it can be computed with coupling, in perturbation series in lambda. It can be computed on string side at 3 level, 1 loop and 2 loop. It was done explicitly. But at the same time, integrability allows you to find an integral equation which actually gives the full function. Sort of exactly in an implicit way, but essentially it allows us to expand as weak coupling or strong coupling to any order in lambda. How from integrability, but actually compute anomalous dimension. Exactly. Now, how to go beyond planar limit? So, for example, what are the 1 over n corrections to that formula? So this is just a Lagen piece. That's integrability doesn't tell us that, and for example, localization doesn't tell us anything about this observable. It's non-supersymmetric, and at least it's not known how to get access to it directly, maybe indirectly in some way. So that would be one interesting question to address. So what localization can give us? Essentially, certain certain observables which are selected by their supersymmetry in particular supersymmetric theories, like n equal 4, n equal 2. So the essential sort of starting point is path integral, say for the free energy on S3 in this case, and S4 and S4 in equal 4 theory, and which kind of localizes just the integral of the constant scalar expectation value of a scalar, and with the simple measure in this case. But there are similar similar matrix integrals appearing in the case of models, which is essentially Young-Mills plus various hypermultiplets. And the simplest example being, say, Z2 orbifold n equal 4 theory, or SUN quiver, or similar theories, say, with symmetric and symmetric representations of hypermultiplets in symmetric and representations. And then what one could find from localization is a free energy. And looking at its expansion in Lagen, one finds coefficients, say, F0, F1, F2, which depend on lambda. And expanding them from localization, one get exact expressions, but expanding them discovers a remarkable fact. So expansion is organized in powers of square root of lambda, which is string tension. So what that means is that this series, for example, for this F1 leading 1 over n correction, it should actually be somehow described by string perturbation theory. And indeed, one could try to identify this leading coefficient as coming from R4 correction on supergravity effective action. And then there are subleading terms which should come also from high derivative corrections. So that's kind of remarkable that gauge theory, through this localization, it knows about, well, it matches what we should expect in AdS CFT, and that's kind of non-trivial. It's not. It now is beyond the planar limit, so we're really looking at subleading correction. So in the case of AVGM theory, same can be done, and one could look at free energy or Wilson loop expectation value and try to go beyond planar limits. So in this case, we have two limits, which I'll be discussing. One is, in fact, it was already mentioned on Monday. We have usual planar limit where we fix analog of Toft coupling, N over K. We take large N, large K, K level of UN. But we can also consider M theory limit where we fix K and then take and then expand at large N. So the aim will be to take localization results and for the Wilson loop or for the free energy, and then try to understand them from dual side. And That understanding will involve, in the case of M theory limit expansion, it involves quantizing M2 branes. So I'll explain why M2 branes appear here, but of course this is central to ABGM theory as kind of theory describing certain M2 brane limit on theory on multiple M2 branes. So essentially, what the idea would be to reproduce localization results for Wilson loop first from quantum M2 brane. So the first question would be, what does it mean membrane? Formally, it's non-normalizable theory, but we will see that indeed the aim is to see that in fact one loop approximation, at least, or semi-classical expansion for M2 brane is well defined and gives results which match localization results from gauge side. So membrane action, in fact, appears before string action in, well, sort of not in exactly that form, but close in the paper by Dirac. And if one looks at this action, one realizes that it's highly nonlinear. There are 3 diffeomorphisms, but 6 components of the metric. So one cannot get rid of one cannot make this action or equation of motion linear and solve them explicitly. It's very nonlinear. And it's also this tension which appears in front. It has 1 over length cube. So it's power counting non-normalizable theory. Plus, there was some discussion of what kind of spectrum that theory may have, and at least in bosonic theory, there are potential instabilities and of this path integral. But so how to make sense of this theory is not a priori clear. But once one looks at the supersymmetric version or supermembrane version of that, in fact, things should be better, and supermembrane theory, in a way, it's very special and unique, and especially in this particular maximally supersymmetric backgrounds like flat or AdS. And the AdS 4 times S7 over ZK background, which is just orbifold of that, that's what is relevant for ABGM theory. And that will be the main focus. So to start from the beginning, so why M2 branes and where they come from? So one possible logic is to look at, say, 11-dimensional supergravity and look at solutions which appear there. And there is a what is called M2 brane solution, which essentially is a background produced by a source, kind of delta function source of a membrane. And one could then look at collective coordinates of this membrane. So near horizon limit of that solution is, of course, AdS4 S7. So looking at collective coordinates, one essentially can rediscover M2 brane action in static gauge, but that's essentially what was constructed before that solution by analogy with Green-Schwarz action directly. So that's kind of globally supersymmetric and kappa symmetric generalization of the Dirac action from membrane. So how it's constructed, one has kind of globally supersymmetric generalization of usual derivative of x. X are embedding coordinates, small m is 3-dimensional index, and sigma is 3-dimensional coordinates. So we introduce this theta, which is spinor, Majorana spinor, 11-dimensional Majorana spinor. And the metric is built out of these p's. So GMN is a target space metric. So in flat space, it's just this. Plus there is C3, which is the 3-form projected again on the world volume of this membrane. So the basic important parameter is this T2, which is directly related to Planck length in 11 dimensions, so or Newton's constant in 11 dimensions. So the membrane tension is 1 over length cube, Planck length cube. So if we have some curved background, there will be dimensionless parameter associated to this tension. Is just length of this AdS scale cube over this Planck length. So it will be dimensionless coupling. So that will be related to n over k, n times k, square root of n times k in the case of ABGM theory. So this whole story is, of course, related by dimensional reduction or double dimensional reduction to the 10 dimensions, 10-dimensional supergravity. So if we just compactify an 11-dimensional circle, we get from 11 to 10-dimensional supergravity, and there is a similar 10-dimensional solution, which is fundamental string, or just wrapping one of these 3 sigmas on a circle, at the same time wrapping one of x's on a circle and fixing x, say 11 or x10 to be sigma 3. One gets from M2 brane action, one gets superstring action in 10 dimensions. So that action just becomes action of 10-dimensional superstring. Or equivalently, one could just assuming membrane has cylindrical form, so sigma 3 is S1, and target spaces also has one dimension being S1. We can just Fourier mode expand, and that action will become 2-dimensional action, plus we're having massless modes plus massive modes in this sigma 3. So truncating to just massless modes will give superstring action. But massive modes in general will be excitations of membrane excitations, which are also relevant. So this is just kind of a general setup. So perturbative string theory is theory of quantum strings. Perturbative M theory sort of should be theory of something like quantum M2 branes. But what precisely that means, that's one of the aims of it's also one of the aims, trying to understand what we can learn about M theory through this, trying to match localization results through the AdS CFT to quantum membranes. So one useful analogy is to think of what we know about N=4 theory in 3 branes. So if we take field theory on multiple 3 branes, we get, for lightest modes, we get essentially N=4 theory on them. If we take one M2 brane, its degrees of freedom on M2 brane is essentially n=8 supermultiplet of transverse coordinates xi and fermions. So it's a scalar multiplet in 3 dimensions. So what happens if we take multiple M2 brane theory? So a priori, it's not clear how to construct this theory, but one could be guided by a dual expectation, that expected dual should be kind of M theory in AdS 4S7. So that was a regional idea of Maldacena, but that theory on a single, well, that theory will be strongly coupled. So that will be like theory on say 2 M2 branes put together. We need an extra parameter, and that was also this. I'm not going to review the whole story, but essentially one very important point that in this case we need an extra parameter to make 3-dimensional theory to have weakly coupled regime, and that extra parameter is this level k of or in ABGM theory, or the dual picture is that we need to take an orbifold of S7 over ZK, which will reduce supersymmetry from n=8 to n=6, but that will allow us, taking k large, to have perturbative gauge theory, which is dual to this setup. So accepting that, we can then take k back to 1 or 2, but then to see how supersymmetry is enhanced, etc., we'll need some non-perturbative states in that, like monopole states in that theory. So anyway, so this is about ABGM theory, and what we need to take out of this is that it describes M2 branes on this on orbifold. So it's Orbifold in flat space is just orbifold of flat 10-dimensional space over Zk, particular orbifold. And the gauge, the fields of this theory are two sets of gauge fields, and there are bifundamental scalars and fermions. So the action is roughly like this. So there are interaction terms. There is a scalar potential. So it's and there are two Chern-Simons terms. And this is important once we start looking at, say, Wilson loops, that we need to know how to construct them. That was already, again, discussed on Monday. So what will be important for what follows is that we have two parameters k and n. So we have two different limits. One limit when we fix k and take large n, and then we dual theory is this, and another limit is string regime, where we get to lambda being fixed and lambda being tension of string theory on AdS for CP3, where CP3 will appear as a base of a kind of Hopf fibration of S7 over CP3 with a circle, and this circle will be identified by Zk. I'll explain this in detail here now. So 11-dimensional metric on AdS 4 times S7, that's how it looks like. But now we want to take this Zk quotient, and that what that means is essentially, if you just write S7 as Hopf fibration over CP3, there is an 11-dimensional circle phi, which is identified normally with 2 pi, but now we identify it with 2 pi k, where k is an integer. So that's just the metric of CP3. This is not that important. So in string limit, what we do, we compactify on this phi, and we go down to for CP3 with this scale and string coupling. These are important relations. So string coupling in 10 dimensions is related to this AdS scale k being k can be thought of as the radius of this circle. 1 over k is the radius of this circle. If we rescale phi back to be 2 pi periodic, then k will appear in front. So so string coupling is related to lambda in this funny way. Lambda 5/4 over n. Lambda is n over k. These are relations which are important to kind of keep in mind. Tension is square root of lambda. So the combination of square of string tension over square of gauge coupling over tension is 1 over k squared. So essentially, 1 over k squared is that particular combination which will play an important role. So membrane tension in M theory expansion corresponds to radius of AdS, or the same as for the sphere, compared to Planck length is much bigger than 1, or that's essentially equivalent to large n for fixed k. In that limit, the tension, effective tension, this rescale tension, dimensionless tension, it's square root of n times k must be bigger than 1. So for fixed k, it's essentially equivalent to large n expansion. Theory in its dimensionless parameter, in 1 over the dimensionless parameter, will be equivalent to 1 over square over n perturbation theory. And that's essentially semi-classical expansion for membrane. So quantizing membrane, expanding in its dimension would be the same as expanding in 1 over square root of n for fixed k. So what we will do, we'll focus on particular observable, which is Hopf BPS Wilson loop, and compared to what we know about its expectation value from localization in ABGM theory, and how we are going to describe it in terms of dual picture. In the dual theory, we will think of membrane, semi-classical membrane, which kind of forms minimal surface, AdS2, inside of AdS7, AdS4, and wrapped on an 11-dimensional circle. So it's membrane of topology AdS2 times S1. So that will represent this Wilson loop. And that's essentially generalization of the string picture where we have minimal surface ending on a circle, say, at the boundary of AdS. So here there is an extra dimension, 11th dimension, and an extra dimension of membrane, and that wraps this extra circle, which ensures that under reduction to 10 dimension, we basically get back our string picture. How to again, there's an alternative way to motivate this. You can think of AdS for S7 being produced by large number of N of M2 branes. That produces the background. And then we put a probe into that background with the probe M2 brane, and which ends on a circle at the boundary. So it's intersection of probe M2 brane with multiple M2 branes over a line. And that's a BPS configuration. So that's essentially why this is how BPS Wilson loop, which corresponds to that picture. So to compute M2 brane, so the idea would be to identify M2 brane partition function with expectation value of this Wilson loop. So M2 brane partition function computed in semi-classical expansion near this minimal surface, which I just described in words. So plan of what I'm going to talk first is this, again, describe localization results and then see how they are matched against membrane perturbation, matched against string results first. And then I also discuss Young-Mills story to put it in perspective. And then look at the same story on membrane side. So jumping ahead, what happens in the N=4 theory, if one looks at expectation value of Wilson loop, how BPS Wilson loop, in large N expansion for fixed Toft coupling, or rewrite it in terms of string coupling over tension, it will be series of terms like this. So that's what you expect in perturbation theory, in usual string theory, if we expand in string string coupling and take tension large. So just leading terms in tension. So it happens to be, what happens is that we get this kind of series. So this series can be summed up in the case of super Young-Mills theory, that's taking exactly known result for this Wilson loop expectation value, and it turns out to be just exponent of this combination. Now I'll explain this in detail shortly. But in ABGM theory, it turns out the plays the role of this exponent is inverse of sine function of G string over tension, square root of tension. So essentially the same combination. So that is 1/k in this case. And that will be essentially prefactor in the Wilson loop expectation value. So produce this prefactor from M2 brane computation. But interestingly, this factor, it has some interpretation in terms of D3 branes, but not at the same level computation. So it's somehow in the BGM theory, this resummation of this series given by this is actually much better understood now than even in N=4 theory. So there are similar results which one can do, what you can find and give M2 brane interpretation also for the free M3, and also for the superconformal index in 2,0 theory, which I'm not sure I will get to that, but they kind of similar structure. So let me start with how BPS Wilson loop. So in N=4 theory, this is a very well-known story. So Gaussian matrix model, localization Gaussian matrix model, gives essentially the exact result for this Wilson loop in terms of N in Young-Mills coupling, and in terms of Laguerre polynomial. And if we expanded this Laguerre at large N for fixed Toft coupling, that's what we get. So at planar limit, it's just Bessel function I1, and then there are subleading term, which is Bessel 2, etc. So the leading term at expanded at large lambda, that's how it it looks like it has exponent square root of lambda and a prefactor which is n over lambda 3/4. And there was some struggle trying to understand what that lambda 3/4 means. And well, maybe I'll comment on that a bit later. But in ABGM theory, similar story. Instead of this Laguerre, what matrix model tells us, in this case, is, as was discussed already, double integral. It gives us up to exponential corrections this ratio of Airy function. So it's normalized Wilson loop, so normalized to free partition function, and the ratio of two Airy functions. So there is a particular depends on n here and k, and there is this prefactor 1 over sine appearing in front. So if we take large n at fixed k, expand the Airy function for large argument, so argument is here n. That's what we get. So we get this left-hand side having 1 over sine 2 pi over k, exponent, and then there are series of 1 over n corrections with coefficients depending on k, with particular coefficients like that. So the interpretation of that expression will be as follows. So that will be classical action of M2 brane on this minimal surface, which is AdS 2 times S1, and that will be one loop correction in M2 brane theory, and that should be two loop correction in M2 brane theory, which is hopefully could be computed as well. So, but that's much harder open question. Whether one could actually reproduce this coefficient as well. Yeah. Yeah, so this expression is valid for k bigger than 2. So that's one of these open questions that membrane computation will actually can be done for any k, 1, 2, and bigger than 2. But this expression was derived, as was already discussed on Monday, it was derived from Fermi gas representation, and that appears to be singular for k equal 1 and 2. So what is the precise formula for k1 or 2? That's a good open question. So string regime, meaning large k as well as n and lambda being fixed, gives this expression. If we just expand that formula in that case, that's what we get. So the action, the exponent is the same. It's just written in terms of that n over k being lambda. Prefactor is now lambda over n, which is 1 over k, and then the subleading correction is 1 over square root of lambda. So that would be that's just the same formula sort of written in terms of string parameters, but how we actually reproduce it on string side, you see this contains n. So we will need to expand that if we want to isolate, say, one loop correction on string side. So that will be the one loop on string side, just square root of lambda, n goes up, but then there will be subleading corrections. Now, it's interesting to compare what we get in Super-Yang-Mills theory and ABGM. It turns out there is a very close similarity if we look at string side in the string limit in both theories. So on Super-Yang-Mills, again, G string is lambda over n. Here is lambda 5/4 over n. Tension is square root of lambda, and the lambdas are defined like that. And on string side, expectation value should be this partition function, expanded near AdS2 minimal surface. In both theories, we have AdS, and the boundary of AdS is circle. So minimal surface for strings in AdS 5S5 and strings in AdS 4 CP3 are kind of having the same AdS2 minimal surface. So the exponent, well, this is the picture of AdS bulk somehow here. That's the boundary. That's the circle of the boundary, and that's the minimal surface for the string. So geometry on that minimal surface is AdS2. And what we're computing is partition function like that on a disk. So it's 1 over G string in front, and Z1 will be containing classical part and one loop correction and sublinear terms. So known results for Young-Mills and ABGM theory, that's how they look like, but rewritten in terms of tension and string coupling on both sides, one discovers they have very similar structure. So essentially the same action in terms of tension, and the prefactor has 1 over G string because of disk topology and square root of tension appearing, but the coefficients, numerical coefficients, are different. And with Jombie, we sort of understood why that similarity actually appears, and I think I will not go into that, but it's basically looking at strings in the similar AdS times internal manifold space, quantizing, one gets very similar structures in terms of fluctuation determinants. So there is certain universality of how this loop correction should look like in both cases because of the minimal surface. And what one learns, there should be the dependence on string tension should be in terms of earlier number of a surface. So here I discussed disk, but more generally it could be a disk with some number of handles. And from string side, just from these worldsheet considerations, prediction should be that in addition to exponent from the classical action, there is a series of terms G string over square root of tension. If we take at each order in G string, strong coupling, large tension limit. Large tension limit. So tension here again is dimensionally square root of lambda. So it's a U for 1 over alpha prime multiplied by square of AdS scale. So again, we expand in small G string at each order of we take large tension limit or large lambda limit, and leads then have this particular structure. So they just G string over square root of tension in terms of Euler number, or the genus of the surface, or number of handles. So remarkably, that matches what we get from Laguerre from gauge side. So if you just take Laguerre polynomial expression for Wilson loop, expand it at large n and then large lambda, yeah, so isolating at each order in 1 over n, large lambda behavior, one gets precisely that. And so from localization, we actually know the coefficients from this expression. We know what are the coefficients. From string side, of course, we only know leading ones, sort of, by explicit computation. So interestingly, what follows from localization from this explicit value of these coefficients is that one can actually resum all these leading terms. So resum all terms which are leading and strong coupling with each other in 1 over n using this expression for the coefficients, and that's what one gets. One gets one loop correction, which I have shown earlier, multiplied by exponent of h, where h is this combination of G squared string over tension, or that lambda 3/2 over n squared. So the idea, the meaning of this is essentially like a small handle inserted at disk topology. So if you have a gas of very small handles, why small handles? Because we take only large tension limit. It's kind of heuristic considerations. But if we just have this gas of these handles, then you would expect that maybe they exponentiate, and that matches that localization prediction. So these are kind of heuristic considerations, but we will see that in ABGM theory, we can actually have a much better explanation and kind of directly following from M to brain theory. So as I just said, confirming this even at next order, like one loop string or torus contribution, one handle contribution, is still it's an open question. How to compute this coefficient, for example, from string side? It would be very interesting. But in ABGM theory, we will know the exact analog of that. So the exact analog of that is this one of this analog of this exponent is this 1/sin. So namely, so what we do again, just to say it clearly, we isolate a leading contribution, which is this, and then at each order in G string, we expand at large tension. And from localization, we know what's the result. The result happens to be 1/sin of this ratio, G string over square root of tension. That gives the coefficients of all these subleading terms. So that's written here kind of explicitly, but the idea is to get this 1/sin somehow. So the claim is that it will come out of one loop M2 brane computation, as I've already said several times. So let's see how that actually happens. So what we need to do is we need to start with M2 brane path integral and expand it near this minimal surface, which is AdS 2 times S1. So in general, M2 brane action, as I said, it's nonlinear. It's not clear how to quantize it. But if we do semiclassical expansion where we have minimal surface, which is non-degenerate three-dimensional metric, we just expand near this minimal surface. It's just like we can do, say, in Einstein theory, expanding. We can't expand near zero metric, but we can expand near some background metric, and then quantize small fluctuations. So that can be done for M2 brane just in static gauge, where here we identify 3 coordinates with 3 target space coordinates, and then quantize transverse fluctuations. So that can be done explicitly, and for that, we basically, at one loop order, we just need quadratic terms in fermions and quadratic term in expanding bosons near this minimal surface. Fermions have no expectation value, so here we just expand in thetas to quadratic order, and fermions will sit in this background geometry. So GAB will be induced metric, in this case just AdS 2 times S1. And this action is kind of explicitly known, so you just will get some determinants of Dirac operators projected to the minimal, to this three-dimensional surface. So all these indices, big indices, are target space indices, and they will know the information about target space geometry is just AdS 4 times S7 over ZK. So we will end up with one loop correction, which is a sum of determinants of these fluctuation operators. So that's explicitly what happens. So the spectrum was worked out for these fluctuations near this AdS 2 times S1 classical solution. So that's a classical action. So the classical action is just tension volume of AdS 2 times length of S1. Length of S1 is 2 pi over 1 over K. And somehow I had some wrong formula. It's 1 over K. We divide over K, not multiply by K. So phi was identified with 2 pi over K, not times K. So 1 over K is the radius. So that's basically, that's important message. So the metric is metric of CP3 in 11 dimensions plus 1 over K squared d phi plus some A, which depends on the coordinates of CP3, but this phi is 0 to pi if 1 over K is extracted. So the radius, the 11-dimensional radius effectively is 1 over K squared. So the modes, like Fourier modes, they will look like n squared over R11 squared, so they will scale as n squared K squared. The mass is squares of mass. So that will be important. That's essentially what is written here. So the spectrum of small fluctuations, they depend on K times n, and with various shifts depending on geometry, which is non-trivial, this induced geometry being AdS 2. So one needs to fix gauges, so static gauge, kappa symmetry gauge, and find those fluctuations in different directions. In AdS 4 is CP3, and one ends up with 8 bosonic, 8 fermionic fluctuations, and then one combines them and gets some ratio of determinants for one loop correction. So classical exponent of classical action times one loop correction. And these are determinants. And then one just uses spectral zeta function to compute these log determinants. So it's very standard story. One important point is that we're dealing with three-dimensional theory. At one loop order, there should be no log UV divergences. Once we compactify, once we Fourier expand in modes, which I was doing here, writing the spectrum, I assume I expect all the fields in modes in this sigma 3, third coordinate. So that's why n is level. So effective theory, which we have on a world volume, is two-dimensional. So we have infinite tail of Kaluza-Klein modes. So it's like string theory modes, level 0, plus all sorts of massive modes with particular spectrum. So once we sum over these modes, all log divergences will go away. But in two dimensions, in principle, you will have log divergence. So that's each determinant will have some log divergent terms in principle. But so the story here is that we need to use, to match kind of three-dimensional picture to two-dimensional picture, we need to use zeta function regularization, normal zeta function. So it's just Riemann zeta function because it's just one circular dimension, S1. Like in the usual quantum mechanics, with path integral, one needs to regularize infinite sums of infinite products. And well, doing this, we end up with one loop correction looking like this. There are all sorts of cancellations happening of finite paths because of boson-Fermion cancellation. And the final result looks like this. It's infinite product of log k squared n squared over 4 minus 1. So in that formula, I'm assuming k is bigger than 2, or kn is bigger than 2, but one could separately do computation for k equal 1 and 2, and now show also the expression. So then using zeta function, this sum becomes this sum, and then we can use Euler's famous relation that sine is a product of 8 zeros, and we end up with this formula. So the effective action is just log of k over 2 pi sine 2 pi over k. So the prefactor is 1 over 2 sine 2 pi over k. And that matches precisely with localization, which was discussed earlier. So for k equal 1, 2, one could do separate analysis of the fluctuation modes, and this one loop correction happens to be 1/4 over 1 in these two cases. So that remains an open question, how to match it to localization, to these two cases. So how to, well, one obvious generalization of this computation would be to two-loop level, where we have particular prediction from localization. And that's how it looks like in terms of one over tension of the membrane. So it's really two-loop correction from membrane point of view. So conjecture would be that localization actually tells us that membrane computation must be UV finite, despite the membrane is not ultraviolet, non-normalizable formally. But also, yeah, so if assuming we can do this computation, discover it's UV finite, though there could be, in principle, there could be two-loop UV divergences, log divergences. At one loop, there are none, but at two-loop, there could be and should be, but they hopefully cancel. And if that happens, we may be able to actually match this subleading term. That is the reason I'm mentioning this, because in Green-Schwartz story in AdS 5S5 and AdS 4 CP3, similar question was addressed for the case of Caspar anomalous dimension in planar limit in 3 level. The two-loop correction in Green-Schwartz action was computed, and also it happens to be finite, despite formal non-realizability of Green-Schwartz theory in these backgrounds. So that gives indication of maybe this maximum supersymmetric case is actually much better behaved, and also there might be some hidden symmetry which we are not aware of in M2 brane theory, which actually constrains the theory, like in this whatever TT bar deformations, where there is some hidden, say, integrability prescribes that you should prepare certain counterterms in certain way, that the theory is actually defined to all orders with a particular underlying S matrix, but despite the fact that it's formally non-normalizable. So something like that may be happening here as well. So the lesson to take is that maybe we should take M2 brane theory seriously, and try to see how much we can learn from it. And here comes an example which is still unpublished, but we can basically do similar computation in ABGM theory, starting from M2 brane generalization of this folded spinning string, which gives Kav-Spanola's dimension, but now doing the same thing for M2 brane. So this is already non-BPS observable without any localization result. But from this membrane computation, one finds prediction, which looks like this. So there is there is leading strong coupling term. There is one loop term, which was discussed 10 years ago, more than 10 years ago. So this is analog of the one loop 3 over whatever 2 pi log 2 correction in AdS5S5. But then there are series of terms which go as 1 over k squared, 1 over k fourth, which would be non-planar corrections. Leading strong coupling large lambda terms at each order in 1 over n. So how can we compare this to something? I don't know. There are no, apparently no non-planar results at strong coupling from gauge side, because we don't have some analog of localization, but that will be example of what we can say more from membrane side. So a similar topic is ABGM free energy on a sphere. Well, again, we have expression from localization, but now we can look, localization expression gives us perturbative part plus instanton correct. Now we can see whether we can match instanton part of non-perturbative part at large n using membrane approach, quantizing membrane in this background. But now we will be looking at instanton, M2 brane instanton and on S7, which will be essentially S3. So it will be generalization of string instanton. Usual in the string limit, one can look at AdS 4 times CP3 and consider CP1 two sphere inside of CP3 instanton, string instantons as Euclidean world surface wrapping this minimal surface, and that gives the exponent in the leading non-perturbative instanton contribution. So kind of generalizing this to M theory limit, that corresponds to the CP1 times S1, this 11-dimensional circle. So the surface is S3 divided by ZK. It's essentially the same CP1 Hopf vibration of S3 with CP1 times the circle, and circle identified just like the same way as I discussed here. So one could do exactly, not exactly, very similar, but actually much harder computation in this setting. So namely expanding M2 brane near this S3 over ZK minimal surface. And then fluctuation determinants reproduced as 1 over sine squared to pi k. So in some sense, what we discussed earlier was a disk. So here it's a minimal surface is a sphere. Times for sphere for a sphere, or for the string, S2 times S1 for the membrane. So in somehow square of this Wilson loop result happens miraculously to give us prefactor in this F instanton, in the free energy of instanton. So here I'm just quickly run through details, but I'm not sure how much time I have. So what is known from localization is that partition function of free energy has perturbative part and non-perturbative part. So perturbative part so far the classical part and 3/2 part is coming from, can be understood as coming from Einstein action, from effective actions of supergravity. That should come from R4 correction. And that should come from one loop membrane. Well, we discussed this with Matteo Biccari in one of our papers, but how to get this A over K term, but I wouldn't say it's understood. It's well understood how we actually reproduce that. It should effectively come from one loop correction in 11-dimensional supergravity where M2 brane propagates in the loop. So that's kind of philosophy behind this term. But non-perturbative, that's how they look like. There are two types of instantons, which are normally mentioned here, which are in stream regime, this is instantons, CP1 and CP3, and D2 brane instanton, which is wrapping RP3 in CP3. So this D2 instanton gives correction, which one of these two. But you see, actually here we have this KO into 1 over K or 2K over 2 symmetry, where N1 and N2 are any integers. And this distinction between the instantons actually in M-theory regime, if K is large, this term is dominating because of minus sign. So this RP3 instanton should not be relevant for large K. But for K1, 2, or small k, both of them are on equal footing. They're mixed up. And jumping ahead, we don't really understand how to match, how to reproduce semiclassics for this RP3. Partly because localization result doesn't have large K expansion. But again, at large K, this term should be subleading. So anyway, there is some mystery here about what that means in M-theory regime. But if we take large K and just focus on this first instanton, which is membrane instanton in M-theory regime, namely this S3 over ZK, we get precisely this prefactor, which I mentioned earlier, from semiclassical computation. So that's again the story. So this is this prefactor expanded. That's its interpretation. It's again summing up leading strong coupling terms at each order in G string, if we think of it as string expansion. And on the membrane theory side, we pick up this minimal surface now embedded into S7. So it's just CP1 times S1 twisted. Do fluctuation modes. So here it turns out fluctuation determinants are much harder. We have some monopole potential. So the fields are charged with they live in a 3-dimensional gauge field or 2-dimensional gauge field, which is kind of monopole on S2. So getting the determinants is harder. And we were guided a little bit by early analysis on the string side in the string limit when when one looks at similar problem for the string. But after all dust settles, the result is extremely simple. We basically get very similar sum as in the Wilson loop computation. And the prefactor, so the effective action is roughly the same and up to the coefficient. And that's what we get. That partition function is 1 over sine squared. Or from localization, it should be 1. But in fact, from string side, there seems to be some subtlety about how we count the zero modes, and there is another saddle. So anyway, so using string side limit and the arguments in that paper, we can fix nu to be 4, and then we match localization. But again, even without that, it's just about this overall coefficient, not about the structure of 1 over K. Now, interesting thing is that this effective action is the same as just partition function of a circle of harmonic oscillator on a circle. So that suggests that the original determinants are much harder. So everything cancels out apart from this small thing, giving this prefix. So that suggests that maybe some kind of localization is at work in 3 dimensions. So we have lots of cancellations, and we end up with much simpler theory governing these fluctuations of this membrane. So again, a subleading term has, again, structure of two-loop correction. With, of course, here this coefficient is different from what it was in Wilson loop, but structure is very similar. And I guess I don't want to comment on RP3, but that remains to be understood. One of the reasons why we do not understand this RP3 instanton is because if we look at membrane fluctuations, if we assume membrane is wrapped on RP3, it will be sitting just in CP3. It doesn't know about this 11-dimensional circle. So that means it doesn't know about 1/k. But prefactor in RP3 case should depend on k. It does depend on k from localization, though in a very funny way, which doesn't allow a large k expansion. So that suggests some puzzle, and so we don't really understand that case. And I guess since I run out of time, I'm not going to say anything about this case, I guess. So here the story is somewhat similar, but somewhat different. So here it's supersymmetric partition function, essentially superconformal index, and kind of giant magnon or instanton contribution into that index, which can be captured by a similar semiclassical computation of M2 brane. So here there are all sorts of, at one level it's very similar, on the other level it's somewhat different because the background involves extra twist. The 11-dimensional background, it has the structure of AdS7 with one circle being identified with period beta, and S4 also has some twist. One of the coordinates is mixed with this of AdS. The reason for that is because we're computing this index, which has extra R charge, and that's related. To preserve supersymmetry, one needs this extra twist. But I guess I probably shouldn't go into that. But I'll just summarize, and when I will summarize, I'll say what one gets here. So here, the structure, the non-perturbative term happens to be having exactly very similar structure with beta playing a role of 1/k. And instead of sine, we get a hyperbolic sign. So let me jump to my, and there is a similar computation for Wilson loop, but let me just skip the details and jump to conclusions, where I will summarize what's the story here. Yes, so to summarize all these cases, let me start with the last one. So what I just discussed was this M2 brane and this particular background with twists, which should be dual to 2,0 with parameters beta and n. Beta has interpretation. If we compactify on the circle, 2,0 reduces to 5-dimensional super Yang-Mills, as was discussed by Kim Young. From 5-dimensional point of view, this index has interpretation of localization free energy in 5 dimensions. So, but yeah, so this is just interpretation, but from M2 brane's side, what we're doing, we're just computing semiclassical partition function on S1 with period beta times S2, and that's what the result looks like this. And that matches localization result. Now, if we do similar computation for M2 brane wrapping AdS3, that will be Wilson loop computation in that 5-dimensional super Yang-Mills theory. Again, it's closely related to this matrix model, which is essentially Chern-Simons matrix model, supersymmetric Chern-Simons matrix model, which appears in this story. And here we get a similar expression with, again, with not sine squared, but just one sign. So in the case which I discussed earlier, AdS4 S7 over ZK, ABGM theory, the story was like this. We have S3 over ZK instanton, which describes non-perturbative corrections to the free energy on S3. So here the structure was 1 over sine squared, where B here is this, where is B? B 2 pi over K. This is the period of this extra 11-dimensional coordinate. And the first computation which I was discussing was for Wilson loop, and that has 1 over sine B, which is this 2 pi over K. I call it B to compare to that beta. Yes. So surprising is that these 4 computations, so free energy, Wilson loop, in 2 different cases, happen to have the same structure with up to some analytic continuation. So precisely why that happens is not completely clear, and one could try to conjecture that maybe that's because what we're doing is we're kind of interchanging AdS with the sphere. So notice that in 2,0 theory we have AdS 7 times S4. In ABGM theory we have AdS 4 times S7. We're doing some analytic continuation, you can kind of interchange the two, and that may be suggesting how, in principle, these computations can be related. But looking at details, it doesn't look completely consistent because, for example, trying to compare these orbifolds, they do not seem to be related by analytic continuation. So we're not able to understand this kind of in a consistent way. But there is definitely some analogy, and it comes out of two completely different stories. A BGM story is not about an index. I mean, localization matrix model is very non-trivial. It's more non-trivial than in the index case. But at least these one loop results happen to be related. I'm just looking if there's anything useful to add here. Yeah, so that's what I mentioned, that about this orbifolds not being the same. And I also mentioned earlier that at the end, the results are very simple. They essentially like this 1 over sines is like what appears in the harmonic oscillator. But why that happens is not completely clear, though suggesting that there may be some kind of effective Bird volume index appearing here and playing some role. So I guess, the final slide is just a summary that these examples are non-trivial tests of AdS for CP3, but it's also test of AdS CFT beyond plane of limit, which is not much what can be done in AdS5 CFT, sorry, in AdS5 S5 at the moment, beyond this half VPS Wilson loop. Even there, we don't know how to compute string side to the same level as we achieved here for quantum M2 brane. So evidence that M2 brane theory is well defined in semi-classical expansion, and that may be giving us also a handle on what is the theory of quantum supermembranes. I already mentioned there is some kind of remarkable relation between completely different QFTs. So there are 2 different angles on that. So we have 3-dimensional superconformal non-abelian Chern-Simons theory on S3. At the same time, we have nonlinear M2 brane theory of abelian 3-dimensional scalar multiplets in curved space. So we are comparing 2 different partition functions and establishing some relation between them. And similar story for AdS7 CFT6, namely this 2,0 theory. It's again captured by M2 branes, but now in AdS7 S4. So it's M2 brane probing multiple M5 brane theory. So I guess I'll stop here. Thank you.
Don't you have to worry, certain level, worry about the connection to the background?
No. The reasons why no, so these backgrounds are very special. So it's AdS times S, and they have maximal supersymmetry, or close to maximal if we take on orbifold. And generically, what one issue which is relevant is the shift of n. The identification of parameters one needs to be careful about, indeed. But geometry will, it's very hard to deform this geometry. So at best it could be level, at best it can be tension, which is changed, how the identification of parameters is related. In principle, one needs to worry about that. And we know there is an issue with what this function, which is called h of lambda in the ABGM theory, already in planar limit, which was fixed comparing to localization. But yes, so how the identification of parameters needs attention, but it's only that. I would not expect geometry being changed. If you put M2 brane in kind of general 11-dimensional supergravity background, yes. So then there could be corrections to the background coming from high derivative corrections on supergravity. Yes. Yes, so the story about that was essentially that you can have three-dimensional surfaces which have actually degenerate metric, which can produce some spikes, etc., which without changing the area much. But for semi-classical expansion, you fix geometry. You're not summing over different geometries. You're not summing. But actually, one lesson, not lesson, but one part of philosophy which comes out of that story is that if we look at string theory, we're summing over topologies. So disk with handle, two handle, three handle. But this sum over topologies actually it's already captured by just semi-classical membrane computation on a given topology or a given topology. So membrane theory incorporates at least in this limit sum over string topologies. So you don't need to sum over topology in the membrane theory, at least to match this perturbative computation. Well, yes. So, well, if yes, so non-perturbative computation, you may need to sum of instantons, different membranes wrapping on different cycles, etc. That is true. But if we just consider this prefactor to that exponent, that is controlled just by given saddle, yeah, membrane saddle.
Any one to four, okay, it's like trivial if one does correlators get exactly the same. And although they're not related by SQuality, they both originate from some sort of single Excel depth function. One of them goes like lambda, the other one like lambda. Very much like the NK and in this case, I don't know if there's any relation to there.
No, I don't know. I don't have any comment on that. But also, I would say that that formula with two terms in the exponent, yes, it does come out of localization, though it's also kind of a bit murky story. But from this M2 brane interpretation, it's very different, as I mentioned. So you have one saddle which is not wrapping S1, another is wrapping S1, and they are not on equal footing. There's no obvious symmetry. So from 11-dimensional point of view, there's no obvious symmetry. And that's a very interesting. Maybe we are just not know, we don't know something. That's quite likely. Yes, because you see, I have a formula which is definitely is defined. I'm not sure where it is. There should be some analog of it here. This formula is actually fine because it's kind of a native continuation. Let's see. Yeah, this one. So yeah, because of this -1, it's essentially inverted harmonic oscillate. So there is, if you take any k being whatever, you can hit the -1. But if k is bigger than 2, n is starting from 1, you never have this problem. But you need to go back if you want to reanalyze k equal 1 and 2, and we did it. You just need to look at spectrum, and there is no any problem with the spectrum. Yeah, yeah. So that just that formula applies to. Yeah. Yes, we didn't discuss 1/6 explicitly. But there are, yeah, here there is a zero mode issue there. You need to smear it. But apart from that, I don't have much to say. But I think it could be done, it could be discussed as well, and it should be, they are closely related. As you discussed, so one is, if we know 1/6, we know 1/2. The other way around, it is not true. Yeah, I would expect a similar structure. Yes.
You have seen that in the case, we have types of non-perturbative. One of it is some sense of light, okay, and the other one is union, correct?
Mm-hmm.
Also, I am assessing the Doppler's function, and I'm able to sum all the I have an hint that there are something more, this theory.
Let me see. Yes, so let me see if I understand what you're saying. Yeah, so essentially I think we're talking about this formula. Yeah, so this from string side, that's the expansion. So you have expansion in small g string. It happens to be organized like this. So at each order, you have 1/t in some power in front of corrections which go as constant plus 1/t plus 1/t squared. So if you could resum each of these, so what we did is just that summing just leading C0, C1, C2, and that gives us this expression. Yes, but if you want to capture two loop term, which was not here. Yeah, the interesting thing is that where is this localization story? Here. If we want to capture this term, so here you see yeah, so that was k is related to, so 1/k squared. Yeah. So 1/k squared was precisely this g 1/k, g string over square root of t. So what that means is that this term, which is two loop on membrane side, or 1/n, it actually contains all series in g string because of k. So if you rewrite it, actually you can put 1k here, it will be lambda, and here it will be k squared. So this is 1 plus 32 over 1/k squared. So there is an extra g, not all terms, but just extra g squared over t term coming from sitting here. So that means this subleading term also gets contribution from each order in the other expansion. Yes. So we will need to know all subleading terms like this plus next one to match this one. Yeah. And of course, there are exponential corrections. Yeah. So interesting thing. So this is sine. So this is not sinh. So in the sinh case, it's like one exponent plus another. But here it's sine. So exponential corrections will be really instant-on corrections to this Wilson loop, which is a separate story which we didn't discuss. But in principle, that should somehow be related to minimal surface where you have membrane wrapping S2 in S7 and also AdS2 in somehow, but somewhat like latitude. Well, sort of. You can have a string wrapping a circle on AdS, but also wrapping a circle in S5. No, of course, latitude is not non-perturbative, but here is really like instant on.